So now that we've looked at the sine bit and we've looked at the exponent, we're going to go ahead in this video and look at the mantissa. So what we've got in front of us here are the two numbers that we started with. We've got the 32-bit number for minus 0.7 and we've got the 32-bit number here for 492.75. Now in order to get the mantissa, we had to count in 1 for the sine, and then we had another 8 bits for the exponent. So that's 1, 2, 3, 4, 5, 6, 7, 8. So that's this point here. So the mantissa starts at this point here. But we've seen before that if the number is a normalized number, then we extend the mantissa because there's an assumed 1 in front of it. So we actually have to extend this 23-bit number to 24 bits. And if it's a normalized number, if it's a normal number, then we have to extend it by a 1. And that's what we've done down here. So we've taken this 23 bits here, which are the 23 bits here after this point, and we've added a 1 on to the beginning, so it's 1 point, all the numbers. So there's actually 24 bits here. Now we've done the same with the second number. You can see that they've got the 3 ones here, which are the 3 ones here, and we've put in an extra 1 here. So this is the bit extension. But we know that as well, if we've got a denormalized number, we don't extend the bit with a 1, we extend the bit with a 0. So we need to know first of all whether the numbers we're going to multiply are going to be normal numbers or denormalized numbers, because we need to know the bit extension, whether it's a 0 or a 1. So let's go ahead and we'll do that first of all in Logisim. So let's create a new circuit here. So project add circuit, and we'll call this one FPU underscore norm underscore denorm. And we'll get into the start menu. So it's going to be relatively simple to figure out whether the number is going to be a normal or a denormal number. So we're going to have to take the two inputs. So we're going to require the exponent for x, and I'll put this one west, and we're going to require the exponent for y as well, and we're going to just have to check and make a comparison with the value of zeros, all zeros. So in order to do that, you can get a comparator. So head to the arithmetic section, and if you head down you'll see something called the comparator there. So we can put the comparator in. I'll go Control C, Control V, and we're going to make the comparator 8 bits, and that's 8 bits, and we'll have to compare it to a value of 0. So we can put in a constant in the wiring section. We'll have our constant and we'll face it east, and it's going to be 8 bits and it's going to be a value of 0. So that's our constant. Control C and we'll Control V, we'll put the same one up there. So we're comparing this number here to 0. If it's true and it is actually 0, then we'll get a high output here on the equal sign. But the way we're actually going to do it is we're going to put in an inverter here, because we're actually wanting it round the other way. So if it's a denormal number, then that value will be high, so in which case it will be low. So if it's a denormal number, it will be low if we take the output from here, and if it was a normal number, the value will actually be high. Okay, so that's all we really need here, and we can put a couple of output pins, and we'll just call them X norm and Y norm. So there's output pin here, and we'll put this east, and we'll call them X norm and Y norm. X norm and Y norm. So that was relatively straightforward. And we'll put this here, of course. The output here, the output X norm, Y norm are just one bit. It's either just going to be a 1 or a 0. And we'll put a little note in as well, so just to remind us. And we can say something, so we're going to have 0 will equal a denormal or subnormal. It's the same thing, denormal or subnormal. And the other 1 will equal normal. Okay, and we can just make those, we'll make them bold. I'll make them 16 and bold. Okay, so that tells us the values that we're going to get out. So that's quite straightforward. So let's go ahead and we'll build the hierarchy for this. So project, and we'll go and grab it first of all. We can go Control X, and we can put it into our norm denorm, Control V, and then we can go to project, edit circuit appearance, and we can change this appearance. So you can go ahead and do this, and you can change the appearance in whichever way you want. So I'll just fast forward this and I'll get this completed, and I'll get you just in a minute. Okay, that's it been created, and I've called it norm denorm. We've got the exponent for the X coming in here, we've got exponent for the Y coming in, and we've got the test whether it's a normal number for X or a denormal number, and we've got the test for the Y as well. So that's us done that. Let's go ahead now and we'll create a new instance, and we'll do the 24-bit extension of the Mantissa and also the multiplication. So we can get into project, add circuit, and we'll call this new circuit FPU underscore Mantissa space +1 space +0. So that's it there. So let's go into main, and we know that in order to build this, we're going to have the two values for the Mantissa coming in. So these are going to be the 23-bit values. So we're going to have the Control C, Control V. So we're going to have our XM and our YM, and these are going to be our 23 bits. And again, we'll place these at the west. And this one here is going to be called XM. Oh. So we're going to have XM, and we're going to have YM. So that's our inputs for our circuit. Now we're going to have to extend these bits, but the bits are going to have to be extended depending on whether they're going to be normalized or a non-normal number. So we can use the bit extender. If you go to arithmetic, now there's one here called bit extender, or it might be somewhere else. Let's have a look and see. There it is there. It's actually in the wiring section. So we've got our bit extender. Now we're going to extend this from 23 bits to 24 bits. but we're also going to extend it depending on a particular value. So it's going to be dependent on whether we get a 1 in at an input, as an input. So we're actually going to have a value up here, extension sign, there it is, so extension input. Okay, so depending on what this input is, it will determine whether the extension is going to be a 1 or a 0. So we can just put the normalized value, so that's a 1 or a 0 in here, and it will determine what that extension is going to be. So Control C, Control V, and we'll do the same for this value here. So it means that this value here is going to be our X norm and our Y norm. So again, we can put those input pins, and these are just single ones, single bits, facing south, and this is going to be our X norm, Control C, Control V, and this one will be our Y norm. So that will tell us how to extend the bits. After the bits have been extended, we want to go ahead and multiply these two together. So if you head to the multiplier here, and the multiplier is going to have to be 24 bits. So it means that the multiplier output, if we have 24 bits here coming in here and 24 bits, then we're going to have a possibility of 48 bits coming out. So the lowest 24 bits of that is going to come out here, and the highest 24 bits is going to come out here. So let's have a little reminder of just where we are in the multiplication phase. We're at this point here where we've got a 24-bit number, and we're multiplying it together with another 24-bit number. Whenever we multiply these two together, we're going to get a 48-bit number, so that's just 24 plus the 24. And the decimal point is going to be this number of places to the left. It's going to be the 23 from here plus the 23 here, so it's going to be 46. So the decimal point is going to be 46 spaces along. So you're only ever going to get 2 digits to the left of the decimal point. Now this is really just common sense. If you think about multiplying, say, the number 5 times the number 7, and you get the number 35. So the number 5 is 1 digit, and the number 7 is another digit. So whenever you multiply them together, the biggest number you're going to get is a 2-digit number. So you're never ever going to get a number beyond 99.99999. So you're never going to get a value of 100 by multiplying together 2 1-digit numbers, and that's exactly the same whenever you're doing the base 2. So you're always going to have a 48-digit number, and the number of digits to the left of the decimal point will always be 2. So let's continue with this in Logisim. So the least significant of the 24 bits is going to come out here, and the most significant of the 24 bits is going to come out here, because this here is the sum, and the carry, that is a carry over to the higher 24 bits, is going to come out here. So we're going to give these names. We'll call this one here, let's see, we'll face that north, and we'll face the label south, and we can call this, let's call it Mant, MSB, because it's the Mantissa and it's the most significant bit. the most significant 24 bits, and again it's going to be 24 bits. And you're also going to have the least significant 24 bits coming out here. So again, we'll just connect that here, and this will be called Mant LSB. So let's go ahead and we'll annotate this so that we remember what it is we're doing here. We're doing the Mantissa bit extension, and the other part is the Mantissa multiplication. Remember as well that you tend to call the Mantissa these days the significant, but I've still stuck with the Mantissa simply because it's a term I'm used to using. So we'll change that to our 16 and we'll put it in bold. Okay, so that's us done this. Let's go ahead and we'll create the hierarchy for this. So what we can do is, we're sitting in main at the moment, so we can say Control X, and we'll put this into Mantissa +1 + 0. Control V, project, and edit circuit appearance. So again, I'll go ahead and change this, and you can go ahead and do the same. So that's our instance completed. I've called it Mantissa +1 + 0. The input on the left is the Mantissa for the X and Mantissa for the Y, and we have the test whether it's normal or subnormal for X and Y, and we have the output which is the least significant 24 bits, and the other output for the Mantissa which is the most significant 24 bits. So between these two here we've got 48 bits coming out. So let's go ahead and we'll take the previous two we've just created, this one here and this one, and we'll just put them into one single instance. So let's call this new instance something like maybe Mantissa multiply. So if we create a new project, add circuit, and we can call this FPU underscore, we call it Mant underscore multiply. So this does the bit extension and the multiplication. So when we're in there, we can grab one of these, and we can grab one of these here. So the norm here, X norm, it's just going to head off and it will go into this point here, and the Y norm is going to head off and get into this point here, and we're going to have our input here which is our exponential for the exponent for the X and exponent for the Y, our input here which are going to be our Mantissa for the X and Y, and our output is going to be our most significant bit 24 bits and least significant 24 bits. So let me go ahead and I'll build this just now. So that's it finished now. We have the inputs here for the exponents for X and Y which are 8 bits, and it goes in here for a test to find out whether the values are the normal or subnormal, and the output from that heads into the Mantissa 1 + 0 which extends the 23-bit input, and that's the 23-bit input for the Mantissa, to 24 bits, and it'll extend it by 1 or 0 depending on the values of these lines here. And then we do the multiplication, and when we multiply it we get the least significant 24 bits here, and we get the most significant 24 bits here. So let's go ahead and we'll create an instance for this. So we'll go to project, edit circuit appearance. So again, I'll go ahead and I'll do this. and I'll get you just in a minute. So that's it created here. We've got the exponent and the mantissa for x and also for y coming in, and at the output we've got the least significant 24 bits of the multiplication, and we've got the most significant 24 bits of the multiplication, and I've called it mant multiply. So it means that we can now get into our top level, which is FPU multiply, and we can grab one of these instances and we can stick it down here, and we can actually connect it up now so we can get the values that we want. So we're going to have the XE and face that east, and we're going to have our XM. You can go ahead as well and connect these up, and we've got the same for the Y values and the same for the most significant bit and least significant bits. So I'll go ahead and I'll put these in just now. So that's it connected up. We've taken the exponent mantissa in here for the X and the Y, and we've got the output here, and we've created a couple of tunnels and called them mant LSB and mant MSB. Now what we'll do is we'll grab one of these, Control C, Control V, and we'll put it down here, and we'll call this little section Mantissa multiply. And that's us completed another little section. So what we want to do is just go ahead and we'll test it and see whether we actually get the right values out here for the least significant bits and the most significant bits. So let me go ahead and I'll change the circuit to do that. So what we want to do is really just look at the two output points here. So we can put a probe in, it's facing south, and we can put the value in. So let's put it in binary, and it's going to be this value here. Okay, and we'll also do the same for the other side here. I'll put it up here because you make it a bit, it's going to be 24 bits here. Okay, and we can do the same for the other side. Control C, Control V, and make it a little bit smaller. And we'll put this Control C, Control V, and we'll put this facing north. We've got that connection. So what we want to do is put the values in that we require. So we'll move this up a bit so we can see it a little bit better, and we'll just make it a bit bigger. So I'll go ahead and I'll put the values in here for our two numbers, and we'll see whether we get the correct values at the output here. I've put the two numbers in here. So in the X we've got the minus 0.7, and in Y we've got our 492.75, and the set has gone high and the enable's gone high, which has allowed us to pass it out through the register here. So we're interested in the output here. So this is the least significant of the 24 bits of the multiplication, and that's the most significant of the 24 bits of the multiplication. So we're going to compare these with the actual multiplication. So let's go ahead and we'll do that now. So I've just copied over the least significant bit, 24 bits here, and the most significant 24 bits. So this is going to be LSB, and this is going to be MSB. So we just want to make a comparison. So this is going to be the lowest 24 bits of this number here. So we've got to count 1, 2, 3, 4, 5, 6, that's actually 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So that's at this point here. Okay, so this number here should be this number here, and if you check, the value's got 0, 0, 1101010001, so, and that's the values that you can see here. And the most significant bit is going to be these 24 bits, and you can see that that's the case. It starts off with 101011, so 101011, and the rest of them there. So it does work, and we get exactly what we require. So let's continue with our design in the next video, and we're going to look at probably the most challenging section, which is going to be the rounding, and also looking at the extension of the exponent. And we can see the extension of the exponent just down here. It goes from this case from 2 to the 7 to 2 to the 8. So we'll talk about these in the next video. Thank you for listening. I'll get you in the next video. Goodbye.